Copper additive manufacturing is the next big leap. But is it truly ready for large-scale production? High reflectivity, porosity, and process instability have held it back for years. But new breakthroughs are changing the game. Are we finally at the tipping point? Let's find out. Welcome to Inside Metal Additive Manufacturing, the podcast that takes you deep into the world of 3D printed metals. Each episode, we break down the latest advancements, challenges, and innovations driving the future of metal AM, helping you stay ahead in this rapidly evolving industry. Today, we're diving into one of the most exciting but challenging frontiers in metal 3D printing: copper powder bed fusion, or PBF. Copper has long been regarded as one of the most valuable materials in engineering, thanks to its exceptional electrical and thermal conductivity. It is used in everything from aerospace cooling systems to high-frequency antennas and energy-efficient heat exchangers. Yet, despite its potential, printing high-performance copper components at an industrial scale has been extremely difficult. In today's episode, we'll explore why copper is in such high demand for additive manufacturing, what has held it back, and the latest breakthroughs that could finally make scalable copper PBF a reality. Why copper PBF is critical for advanced manufacturing. Copper plays a fundamental role in several high-tech industries. Its nearly 100% electrical conductivity makes it indispensable for applications such as electronic circuits, antennas, and RF waveguides. Its high thermal conductivity makes it essential for heat exchangers, battery cooling systems, and rocket propulsion components. While traditional methods like casting and CNC machining have been used to produce copper parts for decades, they have limitations. Casting is often time-consuming and prone to defects, while machining is wasteful and restricts the complexity of geometries. Additive manufacturing, particularly laser powder bed fusion, LPBF, and electron beam powder bed fusion, EPBF, promises to eliminate these constraints. With PBF, manufacturers can create intricate internal structures, optimize cooling channels, and produce near-net shape parts, all while reducing material waste. The ability to print highly customized copper parts on demand could transform industries such as aerospace, telecommunications, and renewable energy. However, scaling this technology beyond research labs and into full-scale production facilities has been difficult. Copper PBF still faces significant technical challenges, which we will now explore. The key challenges preventing large-scale copper powder bed fusion adoption. One of the biggest hurdles in printing copper using LPBF is laser reflectivity. Pure copper reflects nearly 95% of infrared laser energy, which means that most of the energy used in a typical PBF system is simply lost instead of being absorbed into the material. As a result, achieving a stable melt pool is difficult, leading to inconsistent fusion and poor interlayer bonding. To address this issue, researchers have developed green and blue laser technologies that are much better absorbed by copper. These advancements have significantly improved energy efficiency, allowing for more precise and reliable melting. However, industrial adoption of these specialized laser systems is still limited, slowing down the widespread implementation of copper PBF. Another challenge lies in copper's high thermal conductivity. While this property makes copper an excellent material for heat transfer applications, it poses problems in additive manufacturing. Heat dissipates too quickly, causing melt pool instability, rapid solidification, and increased porosity. This results in weaker mechanical properties and can make it difficult to produce fully dense parts. To counteract this, manufacturers have begun using higher laser power densities and optimized scanning strategies. Some have also implemented preheating techniques, which help maintain a more uniform temperature gradient and reduce stress-related cracking. These solutions are improving process stability, but fine-tuning them for different copper alloys remains an ongoing area of research. Beyond process-related challenges, material issues also play a role in limiting scalability. Copper powders are prone to oxidation, which can degrade part quality. Additionally, powder flowability affects print consistency, making it crucial to use high-quality gas-atomized or plasma-atomized powders that offer better packing density and reduced contamination risks. Breakthroughs bringing copper powder bed fusion closer to large-scale production. Despite these challenges, exciting advancements are pushing copper PBF toward industrial adoption. One major development has been the increasing use of electron beam powder bed fusion (EPBF) as an alternative to LPBF. Unlike laser-based systems, EPBF operates in a vacuum environment, which eliminates oxidation risks. It also provides more gradual heating and cooling, reducing thermal stress and improving overall part quality. While EPBF is more effective at processing copper, it comes with its own limitations. The high-voltage electron beams require specialized equipment, and the process is generally slower than LPBF. Nevertheless, for applications where material purity and stress reduction are critical, such as aerospace propulsion systems, EPBF is proving to be a strong contender. Another area driving copper PBF forward is the use of multi-laser systems in LPBF machines. These setups allow for better energy distribution and faster build times, making it more feasible to scale up production. As more manufacturers begin integrating high-power green and blue lasers, we can expect better process efficiency and reduced defect rates. Artificial intelligence and machine learning are also playing a role in process optimization. By leveraging real-time monitoring sensors, AI-driven systems can predict defects, adjust laser power dynamically, and optimize scanning paths, leading to higher quality prints with fewer failures. This level of process control is essential for ensuring repeatability and large-scale production. Hybrid approaches are also gaining interest. Some companies are experimenting with combining PBF and directed energy deposition (DED) to create multi-material or functionally graded parts, which further expands the possibilities for copper in AM. Is copper powder bed fusion ready for full industrial adoption? Copper PBF is making significant strides, but it is not yet at the point where it can fully replace traditional manufacturing methods at scale. The technology is currently best suited for high-performance, high-value applications, where the benefits of AM outweigh its current limitations. Industries like aerospace, energy, and telecommunications are already integrating copper PBF into specialized production workflows, but for mass production of low-cost components, additional refinements are still needed. To achieve true scalability, several factors must align. Green and blue laser adoption needs to increase, and process standardization must improve to ensure consistency across different systems and manufacturers. The availability of high-quality, oxidation-resistant copper powders must also expand, making it easier for companies to source reliable materials. Looking ahead, the next 3 to 5 years will be crucial in determining whether copper PBF can transition from a specialized niche into a mainstream manufacturing process. With continued investment in laser technology, AI-driven process optimization, and hybrid manufacturing, the future of copper additive manufacturing looks promising. So, is copper powder bed fusion ready for large-scale manufacturing? The answer is almost. The progress made in laser absorption, process stability, and defect control is bringing this technology closer to industrial adoption. However, cost, scalability, and standardization remain challenges that need to be addressed before copper AM can become a primary manufacturing method for mass production. What do you think? Is copper PBF the next big revolution in additive manufacturing, or does it still have too many technical hurdles? I'd love to hear your thoughts. Connect with us and share your insights. If you enjoyed this episode, make sure to subscribe for more deep dives into the world of additive manufacturing and advanced materials. Thanks for listening, and I'll see you next time. Inside Metal Additive Manufacturing, the podcast.